All right, so we've been doing 6-1, and you guys should have wrapped up that Math Excel last night. 6-1 was confidence intervals, and in all of those problems where we used the standard normal distribution, our z-scores, we knew the standard deviation of the population. In this section, you do not know the standard deviation of the population. All you're going to know is the standard deviation of the sample, and that's going to be the difference between the two critical values that you're going to use in the two tables, okay? So if you know standard deviation of the population, it's Z's. If you do not know standard deviation of the population, it's going to be T's that we're going to use. All right, so that's what this first slide kind of talks about. They're on your desk, Hannah. Okay, so couple properties you need to know first about a T distribution versus a standard normal distribution. So a T distribution, we're going to use T sub C to represent critical values. If you want to find what a T value is, it looks very similar to how we calculate our Z-scores. It's a mean of our sample minus the mean of the population, all divided by, now we've got the S, which is our sample standard deviation, divided by the square root of n, where n is our sample size. Properties, you can just kind of like bullet point these if you want to. Mean, median, and mode of the T distribution are all equal to 0. That's the same as our Z-scores. It's also going to be bell-shaped and symmetric about the mean. Total area under the curve is 1. Okay, so again, all similar to our Z-scores, our standard normal distribution. Number 4 is where it starts to look a little different. The tails of the curve are thicker, which means that on the ends of your bell curve, it's going to be higher up off of your axes. It's not going to be quite as obvious as an asymptote. It's going to be a little thicker on either end, which tells us that we're going to have more data in the ends of our distribution than we saw with our standard normal table. The standard deviation varies with the sample size, but it's always going to be a number bigger than 1. We know that from our Z-scores as well. So a lot of similar properties with these. Abbreviate, bullet point, whatever you want for those. Okay, anybody have it? Okay, so really similar to our Z-scores except number 4 there. We're talking about the thicker tails. At the bottom here, this picture's out of your textbook. It kind of shows you what those thicker tails look like. So the blue curve is the standard normal curve. And then we've got a couple different ways this can look. We'll talk about degrees of freedom in a second. But you can see how far off the axes these tails are, which means we're going to have a greater percentage of data in these low ends and the high ends than what we saw with our Z-scores. Degrees of freedom. You need to write that down. Degrees of freedom is n minus 1. Degrees of freedom is what we're going to need to find in our table to be able to find our critical value of T. Degrees of freedom has to do with how many choices you have for each piece of your sample, where n is the sample size. We don't do a ton with degrees of freedom other than use it to find our T-scores. If you went into a higher level statistics class, you'd get a little bit more involved with what degrees of freedom means and where it can be used. But for right now, you just need to know that means n minus 1. So let's say we wanted to find a critical value of T using that table. All right, so on your table, some of these here, let's say we have a 95% confidence level, so 0.95, and we have a sample size of 15. You first find the degrees of freedom, which are always your sample size minus 1. So here it's 15 minus 1, or 14. So then on your t distribution, you're going to find the row that is 14, and then you're going to go over to the appropriate confidence level. So then you should be able to find this value on your chart, 2.145 for 14 degrees of freedom and a 95% confidence level. You guys see it? Okay, so the one below, you want a 90% confidence level and a sample size of 22. So what are my degrees of freedom that I'm going to look for? What row? $21. And then this is a 90% confidence level. So you're going to look at row 21. You're going to go over to 90%, and you guys should see 1.721. Does that look good? Okay, and that's going to be our critical value for T. If a critical value, or I'm sorry, not a critical value, if a degree of freedom is not listed here, like, I don't know, let's say my degrees of freedom are 72. That's not listed. You're going to look at the value that's closest to it, but smaller than the degree of freedom that you need. So if my degree of freedom that I needed was 72, I would use 70 on my list. That's the next closest that I have that's smaller than the degree of freedom I have. Does that make sense? Okay, so if it's not listed, which most of the ones you guys have will be listed, you won't be dealing with super huge data sets. You just look at the one that's closest but smaller than it. All right, so now we're going to find things that we did with our z-scores. A lot of this is going to look really, really similar to our other confidence intervals. So we're going to find the margin of error. We know what margin of error is. It is the difference between our sample standard mean and then potentially plus or minus from that what we're estimating our population mean to be. In this problem, again, we do not know the mean of the standard deviation. So what we're going to do is our critical value of t here instead of our critical value of z. So we're going to find that on our table. And then we're going to multiply it by the standard deviation of the sample, that's s, over the square root of n, where n is your sample size. Okay, so margin of error, critical value of t, times the sample standard deviation divided by the square root of n, where n is your sample size. All right, so things we could do with this. Let's find the margin of error first. We'll practice that. Before you can find the margin of error, you need the critical value of t. Before you find the critical value of t, you need the degrees of freedom. That's always going to be our first step. So degrees of freedom is n minus 1. So in this case, our n is 16. 16 minus 1 gives me 15. So now you're going to look on your t distribution for degrees of freedom 15, so row 15, and then you're looking for a confidence interval of 95%, 0.95. And you should see 2.131. Look good? So that is our critical value of t. Now we find margin of error. E is equal to my critical value of t times the sample standard deviation, 5, divided by the square root of n, square root of 16. You can go ahead and type it in your calculator. 2.131 times 5 divided by square root of 16, or 4. And my margin of error is 2.66. So then that'll help us in a few minutes. We'll create that confidence interval using that margin of error. All right, you guys try the one at the bottom. Find the margin of error. All right. should get 4.54 approximately. All right, any questions getting margin of error if we've got a t distribution? Great. Next slide on your paper is we have a confidence interval, which we'll be creating in a minute. We want to work backwards and find the sample mean and the margin of error. There is no difference in this problem versus what we did with the z-scores, the standard normal table. So your sample mean is going to be right in the middle of your confidence interval, and then your margin of error is going to be the difference between that sample mean and each end of your confidence interval. So we'll just do one of these. If I want to find the sample mean, it's my midpoint or my average of the ends of my confidence interval. So we're just going to add them up. Divide by 2. Find that midpoint. 14.7 plus 22.1 divided by 2. I get the sample mean is 18.4 that was used for this interval. And then if I want to find the margin of error is how far that sample mean is from each of those endpoints. And it doesn't matter which way you calculate it because 22.1 is going to be the same distance as 14.7 is from it. So if I were doing it, I would probably just do 22.1 minus 18.4, my biggest end of my confidence interval minus my sample mean, which is in the middle. Not the only way to do it though, for sure. And you should get the margin of error is 3.7 on that one. Do you remember doing that with the z-scores? Finding the middle, finding the difference. Okay, so same if we've got a t distribution, nothing different there. All right, so now what we're going to do is we are going to create that confidence interval. These steps are pretty much the same that we did back in the last section. The biggest difference is when you're finding the margin of error, you're not using your z table, you're using your t table, okay? You do have to know the sample mean and the sample standard deviation. They're telling you up here, this is how to calculate them. We did this way back in like chapter 2. You can do the sample mean pretty easily by hand. The sample standard deviation though by hand, remember that's the big one with like all the tables where you do the deviation and the deviation squared and you sum them up. So if we need to find that, we'll probably just be using the calculator to do it. Once you have those, you find degrees of freedom like we practiced. You find the margin of error like we practiced. And then just like with our standard normal distribution, we're going to take our sample mean and subtract the margin error. So sample mean add the margin of error. And all of this is estimating still the population mean. That's what we're looking for. We're trying to get that confidence interval. We're going to be whatever percent confident that our population mean is located within this interval. All right, so we're going to do this one together. It says you randomly select 16 coffee shops and measure the temperature of coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. We're going to construct a 95% confidence interval for the population mean temperature of coffee sold. Assume the temperatures are approximately normally distributed and interpret your results. All right, so let's start kind of pulling information that we're given here. 16, what is 16? What variable? It's our n, that's our sample size. What's 162? That's our sample mean, so our x bar. What's 10? Okay, and remember, there's going to be a big difference now between population standard deviation, which is z-scores, and sample standard deviation, which is t-scores. Sample standard deviation, you are using the s, not the little mu, okay? And it's 10 here. 95% confidence interval, that's my C, 0.95. Okay, so that's everything I was given. We were also told that it's normally distributed, which again, that's one of the conditions for all of these things to be happening. All right, can you tell me now from that what the degrees of freedom are? It's going to be 15, one less than your sample size. If you have degrees of freedom and you have a confidence interval, you should be able to find a critical value of t. So we're going to look at row 15, 95%. This is one we used earlier, 2.131. Once I have a critical value, I can find the margin of error. So we're going to calculate E, 2.131, my critical value, times my sample standard deviation 10 over my square root of n, square root of 16. Type it in your calculator. And it looks like all my temperatures are rounding to 1 decimal place, so we're going to round our margin of error to 1 decimal place. Just going to follow whatever the data is saying as far as the rounding goes. I get to 1 decimal place 5.3. Good. Okay, and again, everything's temperature here, so the margin of error is 5.3 degrees Fahrenheit, if I'm going to label that. So now to find the confidence interval, we're going to take our x bar and we're going to add and subtract e. And that'll tell us either end of our confidence interval that we're looking for. So x bar here was 162. Add and subtract the margin of error, 5.3. And that's going to give us an estimation for the population mean. So 162 plus 5.3 on one end gives me 167.3. 162 minus 5.3 gives me 156.7. If you had to label those, again, they are both degrees Fahrenheit. And there is your confidence interval. Remember, the confidence interval is estimating, again, the population mean. So when we go to interpret our results, now we want to kind of be thinking about what are we estimating. So remember, there were two ways to word this. We can say we are either 95% confident, or you can say there is a 95% probability. I'm going to say I am 95% confident that the population mean of coffee temps, in this case, is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. Okay. Really, really similar to the z-test, right? And our standard normal curve. Wording that the same way, margin of error is going to be the biggest difference. Finding that critical value using a different set of data for that. All right, on the back, you guys are going to try this next one. Now, in this next one, it doesn't say what the confidence interval is because we're going to do it 3 different ways here. At the bottom, we're going to use a 90, a 98, and a 99% confidence interval. So I'm going to assign different confidence intervals to different groups. Hannah, do you want to work with these guys here? Okay. So I'm going to have this group do the 90% confidence interval. I'm going to have this group do the 98% confidence interval, and you guys are going to do the 99% confidence interval for the data. And then we're going to compare your results, okay? So find a confidence interval for your given percentage using the data listed. We'll put them up and we'll compare. The confidence intervals that weren't yours. There we go. And then we're going to make a quick statement comparing these. All right, so what do you notice as my confidence level increases as to what's happening with these intervals? As the confidence level increases, what happens to the interval? Go ahead, guys. Yeah, so the max is getting higher and the min is getting lower. So the width in general is getting larger. So maybe write that down. The width increases as the confidence level increases. So I think I mentioned this before. Why would we not want to use a 99% confidence level all the time? Well, it makes us really confident But a wider interval means our evaluation of where that population mean is located is not as great of a set of information that we're receiving, because the interval is so wide, it really doesn't narrow down where that population mean can be. It doesn't give us a great estimate. So you get a better estimate as we look at a lower confidence level, but then to balance that, you have to know that you are less likely to contain that population mean. So it's like this fine line we're walking. Lower confidence level, better estimate. Higher confidence level, less of an estimate. The interval gets so wide. So you kind of have to decide what your confidence level is going to be as far as what would be appropriate for the data set that you're analyzing. Decide what's best. Okay? Questions there? All right. So on your paper, on the right side, those two slides actually go together. You guys have two stem and leaf plots of data, and then right above that, you guys have this little blurb about what that data represents, okay? So it says 2 footballs, one is filled with air and the other one's filled with helium, are kicked on a windless day at Ohio State University. There are 10 practice kicks. Those practice kicks are not part of the data set. And then after that, there are 29 more kicks. So what you're seeing in the stem and leaf plots are they've filled 2 footballs up, one with air, one with helium, and they kick them 29 times. And they have recorded the distance in yards that those footballs are traveling. We want to find a 95% confidence interval for each football. Okay, so one for air, one for helium. Now, the biggest difference between this problem and the one that you guys just did is in the problem that you just did, you knew the sample mean and you knew the standard deviation. We do not know that here, which means you guys have to figure it out. So what you're going to need to do, and you can find the sample mean pretty easily by hand, but we said the sample standard deviation is a little harder. You guys are going to use your calculators. So the first thing you're going to do with your calculator is you're going to take your stem and leaf plot data and you're going to put it in L1. Then you're going to choose one variable statistic. So that's under stat calc. It's the first option. That will give you the sample mean and the sample standard deviation. So you're going to have to do that for both helium and air. Once you have those, then you can construct both of your confidence intervals. Okay, so I'll walk around, I'll help you with calculators. Our goal is to get all this up on the board or up on my screen in a few minutes here. So go ahead and try it, get your sample mean, get your standard deviation, and then put those together to get a couple confidence intervals. One for a football that's filled with air and the other that a football that is filled with helium. I'm gonna check these real quick. These should be your X bar and your S that you're getting from the calculator. Just double check those are right before you move on to the next step. If you didn't get those, or it's really close but not exact, you might have just put a data value in wrong or missed a data value. That's likely, so just double check those. Okay, and then use both of those to find your 95% confidence interval now. All right, we about ready to check, maybe? Okay, so do you guys have that N is 29, so degrees of freedom is 28, and then the critical T value is 2.048 for both of these. That doesn't make a difference where your sample mean and your sample standard deviation are. That's just the original set of information. So then I've got the error for both of these listed, should have been the next thing you calculated. So the error for air is about 1.5 if I round to 1 decimal place. And the error for helium, I got 2.4. And then taking that, adding and subtracting it to my sample mean, 26.8, 27.5, you get your confidence intervals at the bottom. So for air, your confidence interval should be 25.3 to 28.3. Again, I rounded to 1 decimal place. You might have rounded to 2. Yours is more exact, then that's fine. And then for helium, it should be 25.1 to 29.9. Questions getting those? Okay, now there was a question at the top. It said, do your intervals overlap? Do we have any overlapping numbers here? If we were to like graph these on a number line, would they intersect at all? Yes. Okay, so write that down. Do they overlap? Yes. What does that mean about the population mean? Well, it means that potentially that population mean could be the same. So the mean for air could be the exact same population mean for helium, which means, would it actually matter what I filled the football with? Maybe not, if the mean is exactly the same, right? Okay, so it gives us the possibility that the population means are the same number. Maybe not, but they could be. Okay. Since Megan's not going to be here tomorrow, do you guys just want to do the last slide and be done with it? We don't do it tomorrow then? We'll do it for Megan. Okay. So the last slide just kind of summarizes when we do the test with the Z and when we do the test with the T. In both cases, your population needs to be normally distributed, or you need to have a sample mean greater than 30. So a lot of these problems we've been doing, notice there was like a little kind of parentheses. Assume that the population is normally distributed. They're telling us that. If it's not either of those, you don't use either test. You cannot do a sample test based on that. If you know the population standard deviation, you use the standard normal test with the Z. And if you do not know the population standard deviation, you use the test with the T. So notice the margin of error, really similar formula in both sections. The difference is we find our critical value from the standard normal test, our Z chart, versus we find the critical value using the degrees of freedom from our T chart. So the last slide on your paper just is asking you to figure out which of the two do you use. Okay, we're not actually going to write the whole test. So the first one says, you randomly select 25 newly constructed houses. The sample mean is 181,000. The population standard deviation is 28,000. Assume construction costs are normally distributed. Should you use the standard normal distribution, the T distribution, or neither to construct a 95% confidence interval? What do you think? Z, T, or none? Well, let's kind of go through the flow chart. Is the population normally distributed, or do I have a sample size bigger than 30? It's normally distributed. So yes, I can use one or the other. So we've eliminated neither. Do I know the population standard deviation? Yes. So because I know the population standard deviation, we are using the standard normal distribution or your Z chart. So you would find the critical value of Z to find your margin of error and go from there. Okay. The one below it, you randomly select 18 adult male athletes and measure the resting heart rate of each. The sample mean is 64 beats per minute with a sample standard deviation of 2.5 beats per minute. Assume the heart rates are normally distributed. Should we use a standard normal distribution, a T distribution, or neither to find a 90% confidence interval? Okay, so first question, do I have a sample size bigger than 30, or is my population normally distributed? Is one of those two conditions met? Which one? Again, it says it was normally distributed here. Do I know the population standard deviation? I do not, but I know the sample standard deviation. So if I know the sample standard deviation, which test am I using? Which distribution? T distribution. So you would find degrees of freedom, you would find your critical value from the T distribution and use that to get your margin of error. All right, that's it for 6-2. So 6-2 Math XL is due on what day? I don't know. Let's find out. Sunday nights. I'll do the cell phone lotto. Tomorrow will be a Math XL work day for you guys. You'll get your quizzes on Thursday.